Okay, so we are going to do a question on invertible matrices. We have a matrix A. We know that we have a matrix A, which we are getting is real and is invertible. Now we need to show that a matrix that we build A transpose plus A transpose A is also invertible. What we will do, we're going to look on the kernel of that matrix and show that it equals to 0. This means that the rank is full. This means that this right over here is invertible. And of course, A square. So this is also square. So let's show this. Let's take a vector in the kernel and we want to show that x must be the zero vector. Must be the zero vector. So if x is in the kernel, I can say that this must equal 0. Okay, so 0 is equal to right? The inner product. Because x is the zero vector and an inner product with the zero vector. And because this is the zero vector, x we don't know is the zero vector, but this is the zero vector. An inner product with the zero vector is always 0. We want to show that x must be 0. Now this, from linearity in the first argument, we can say that it equals the first part with x plus the second part with x. Now look on the adjoint. We can take this and move it to here, and this is moved to here. Just take the adjoint, and we are over the real numbers, so take the transpose. So it is A transpose x, A transpose x, plus AX and A transpose transpose, so it's AX. But note that this is the same vector with the same vector, and it's an inner product. So this is the norm squared. But the norm equals 0 or something greater. So in order for all this sum to be 0, we must have that both these terms are 0. So ax squared is 0. In order to be 0, we need that the norm of ax will also be 0. But wait a minute. How do I get from here to that I want to write x equals 0? But how do I get to this? Okay, if the norm of ax equals 0, the norm is greater or equal to 0, and it's 0 just for the 0 vector. So from here I can conclude that ax equals 0. But how do I get to x equals 0? Remember that a is invertible. If a is invertible, so a equals 0, I can take from the left, let's multiply it by the inverse. So it's a inverse ax equals 0. Or if you want, a inverse 0. So from here, we're getting I. So it's x equals 0. And this is exactly what we wanted. We wanted to show that the only vector in the kernel of this matrix must be the 0 vector. Therefore, the kernel of this matrix has only the 0 vector, so its dimension is 0. And from the rank nullity theorem, I can conclude that the rank of this matrix, of this square matrix, is full. And if this rank is full, it means that the matrix is invertible. So this matrix, as needed, is indeed invertible. So this is it. Thank you very much. If there are any mistakes or corrections, please tell me. And that's all.